Hello and welcome to today's webinar, 3D Printing 101. In this webinar, we will cover the basics of the FDM and PolyJet 3D printing technologies that are available through GoEngineer and our Stratasys partner. My name is Tyler Reid and I'm the manufacturing specialist here at GoEngineer, and I will be spending the next 20 to 30 minutes going over the basics of FDM and PolyJet. We're going to go through a quick overview of each technology. And then we're going to go a little bit more in depth how each of the machines work. Then we're going to talk a little bit about the materials, differences in materials, and a little bit about applications, and we'll follow this up with a question and answer session. We are broadcasting this in webinar format, so all viewers who are watching this live, you're free to ask questions, but please do so through the chat window. All viewers will be muted throughout the session, but I definitely want to take your questions near the end. So let's jump into the overviews. FDM. FDM stands for Fused Deposition Modeling. This is a 3D printing technology invented by Stratasys in the mid-80s. It uses real thermoplastic materials as the printing substrate. The most prevalent material that we use is ABS plastic. A lot of designers and engineers are already familiar with ABS plastic and using it in a multitude of projects. The great thing about having real thermoplastics is that the specs are known. We can go to matweb.com or we can go online and we can get basic information on these plastics, which is great when it comes to deciding on a material to use. Outside of ABS, we can also print polycarbonate, nylon, an electrostatic dissipative ABS material, PPSF, and even ULTIM. FDM is known for printing functional, durable, and industry-ready parts. So when we talk about the applications, a lot of the applications I'm going to be talking about will be tooling and manufacturing related, beyond prototyping. The FDM parts can withstand high stresses, high pressures, high temperatures. They can be used in corrosive environments, and they can even be used in flight in some cases. The FDM printers are office-friendly technology, and that means I can have an FDM printer sitting alongside me in my office, in my cubicle, and it can be running throughout the day. It's very unique in the 3D space, and it's actually an attribute of all of Stratasys printers. On the PolyJet side, there's a big difference in materials and some of the advantages and disadvantages. So PolyJet, I may use the word object interchangeably with PolyJet throughout the presentation, and if I do so, apologies for the confusion. Object is a line of PolyJet machines. The PolyJet technology, instead of using a real thermoplastic, uses a high-performance resin, a liquid photopolymer. These photopolymers can be mixed and matched to create different materials, and we can get very different quantitative qualities on these materials. We can print in a rigid or a flexible material. We can go opaque or translucent. We can go grayscale or full color. There's lots of options in the material selection on the PolyJet side. Unique to PolyJet in the 3D printing world is the ability to print multiple materials at the same time. So if you look at the image on the screen, we've got a halo character there, and this guy he stands about 18 inches tall in real life, and he's printed in several different materials in one job. His armor is hard and opaque, and some of his undersuit is like a rubber-like material, and that's printed all in one. PolyJet is known for its high feature detail and great surface finish. And that's one of the unique attributes of the PolyJet side is parts that look great, have small features, and have great surface finish without any post-processing. So that's it for the basic overview. Let's talk a little bit more how each technology works. FDM, the Fused Deposition Modeling, uses melted extruded thermoplastic. So here's a diagram of a basic machine. You have a build material cartridge. That cartridge is really similar to, say, like a weed whacker spool. It's a spool of uh, extruded thermoplastic, ABS, polycarbonate, ULTEM, whatever it is. That's fed up through the machine until it hits a heater block. And inside the heater block, the plastic is melted and then it's extruded through the tip. So this entire system can be really thought of as a complicated hot glue gun. But instead of glue, we're using plastic. So if you can imagine having the ability to very accurately take a hot glue gun and build up a model layer by layer by layer, that's essentially what the FDM machines do. Notice we have two tips here. One is for build material, and the other is for support material. So here's another quick representation that gives some numbers to the equation. We've got our model and our support tips. The model material is extruded out layer by layer. Obviously, 3D printing is an additive manufacturing technology, which means we start from a blank slate and we build our models up, okay? And we build it up layer by layer. These are discrete layers, and they actually are given values in height. So our machines, throughout the spectrum of the machines that are available, we have different capabilities in Z resolution. The coarsest we can go is 13 thousandths of an inch slice height. The finest we're capable of right now is 5 thousandths of an inch slice height. Most machines give you an option to choose what slice height you want, 5, 7, 10, or 13 being amongst the options. We're given that option because really we print parts for different reasons. Sometimes we need a very quick part and it will sacrifice some surface finish for that, and we might print in 13 thousandths of an inch slice height. Other times we need a part to look as good as possible, and we're willing to spend a little more time printing it, and we'll print it 5 thousandths of an inch slice height. The way these printers work is they'll print 2 layers of model material, and then they'll go and do a tip clean, and we'll print 2 layers of support material. So I have a quick video here to demonstrate what's going on. This is the view into, I believe it's a Uprint SE Plus. It may be a Fortis 250. It's a Uprint SE Plus. We have our build tray, which is a black tray. That's what we print on. At this point, we've started the print. It's taken us less than 5 minutes to process our STL file for printing and send it over the machine. The machine, if we've recently changed the material, it's done a self-calibration. There's no calibration on my part as the operator. And we start our print. So as this prints along, we're going to start to notice 2 colors of material start to appear. We have a white color and kind of a root beer color. The white material is the model material. This is the material that's being used to print the end product. Okay, so it looks like we got a wrench there. The root beer color material is the support material. And that support material is there only to support where needed. So this allows us to print any geometry imaginable. We can print undercuts, we can print internal passageways, we can print entirely enclosed voids if we want. That negative space is filled with the support material. The support material is sacrificial, meaning once we take this print out of the machine, we're going to remove the support material. In most cases, that support material is actually water soluble. So I would take this wrench, I would throw it in our heated bath, and I'd come back in a couple hours and I'd have a working wrench. Okay, notice we've got 2 parts here that are really meant to move in relation to each other. That's how these crescent wrenches work, right? We spin that little thumb screw and it opens or closes. Those parts right now would not move because everything's kind of fused together with that support material. But once we dissolve that support material away, we can actually have 2 parts that move in relationship to each other and no assembly required. This wrench, judging by the machine that it's in, it's about an 8-inch long wrench. That print would probably take about an hour and a half to give you an idea of the time. Let's jump over to PolyJet technology. So on the FDM side, I use that hot glue gun analogy. I'm going to use a different analogy for the PolyJet machines, and that's for a regular old inkjet printer. So almost everybody has an inkjet printer at home, and we know how to use them, right? We got a printer driver, we have a machine with a print head in it, and we feed in cartridges of ink. And we only feed in 3 or 4 or maybe 5 cartridges of ink, and the printer drivers mix those inks together to achieve millions of different colors, right? So on the PolyJet side, the analogy goes pretty far. We have a machine with a print head, or maybe 2, or maybe 3 print heads. We have some ink cartridges or material cartridges. We load up a basic number of cartridges, and the printer software can mix those cartridges, mix those inks together to create new materials. One piece of hardware that's different is that we have a UV floodlight. And that UV floodlight cures the photopolymers, cures the material after it's been dropped down. So let's take a look at this working. I'll pause it very quickly here. So we have a build envelope, it's a build tray. In this particular machine, the build platform will actually move down between layers. The layers on the PolyJet side are much finer than on the FDM side. So FDM, we talked about the finest resolution in Z being 5/1000ths of an inch. Well, on the PolyJet machine, the finest resolution in Z is given as 16 microns, which is about 6/10,000ths of an inch. So the print head is going to sweep across the build platform, and it's going to deposit droplets of material. It's going to follow it up with a UV flood lamp that cures all of that material at the same time. So one of the cool things about the PolyJet machine let's watch through that one more time. So one of the cool things about the PolyJet machine is that it will actually print, say, about a third of that platform in the same amount of time as it would print just a quarter of the platform. And that has to do with the width of the print head and having to move across the entire platform, and the use of a flood lamp instead of a finite laser that has to trace the entire path of the part. So the throughput and the printing speed on the PolyJet machines is very good. Let's talk a little bit more about the materials. We've touched on the basics. We'll go a little bit more in depth. The materials on the FDM side, they're real thermoplastics. They're known for their durability and their stability. They're great for prototyping in all circumstances. Functional prototypes, fit and assembly prototypes, and again, prototypes that need to withstand stresses, pressures, corrosive environments, etc. The materials can be opaque. We have 9 different colors of ABS material. Some of the ABS plastics are translucent. We've got a translucent red, amber, and clear. We like to say that the FDM materials are functional. We have an anti-static material. We have materials that are specifically meant for high strength, high temperature environments. Our PPSF material has a heat deflection temperature of 370 degrees Fahrenheit. We have very strong materials, measuring up to 15,000 psi. We also like to say we have industry-ready materials, meaning that they can be sterilizable and they can be used alongside food and drug environments. And we also have our Ulta material, which is FAA certified for flame, smoke, and toxicity. All of the FDM parts can be mass finished, much like other plastic parts on the market. So they can be tumbled, they can be polished, they can be burnished, they can be plated and painted. On the PolyJet side, a lot of the differences in the materials are qualitative. We describe the materials and their qualities. So we can print rigid material that's either opaque or completely transparent. And we can also print full color spectrum now. So with the new machine, the Objet 500 Connex 3, we have 3 print heads and we have a color palette. We can print hundreds of colors, which is really great for uh, marketing parts and prototype parts, and even printing parts that show the results of, say, an FEA analysis. We can also print flexible parts in a rubber-like material we call Tango. The flexible parts feature high elongation, high tear resistance, and we actually have control over the shore value, anywhere from about shore 27 to shore 95, which is great for simulating buttons, gaskets, seals, soft touch surfaces, etc. We have some medical and biocompatible materials that are being used extensively throughout the dental and medical industries. And we have the ability, again, to combine these materials to achieve all sorts of different results. We call these digital composite materials. One example is that rubber-like material with different shore values. Other examples are the full color spectrum and some other hard opaque materials with different attributes. Some of the materials that I don't have listed here are a little bit newer. One's called Endure. It's a polypropylene-like material. Another one is called digital ABS, and this is a digital material available on the Connex machines. It's an ABS-like material that features high strength, relatively high temperature resistance. It's being used right now for short-run injection mold tooling, which is very impressive. So speaking of that, that's a good application. Let's talk about some other applications that we're seeing here. Now, I should give the warning, this is going to be a very brief intro to the applications, but really the applications are the most important, right? We're not buying machines based on the technology, we're buying machines based on the applications. And so this webinar only goes so far. We have a 3D Printing 201 webinar that deals more into applications, and we have some 3D Printing 201 specialty application webinars that you should find on our YouTube page. So some of the top applications, we'll talk about FDM and PolyJet best fits, because really it should be clear by now that the parts coming out of each machine, they're different. The FDM side with the thermoplastics, they're stronger. You know, they're better suited for industrial tooling and manufacturing type applications. Where on the PolyJet side, they're more suited to the aesthetic applications or parts that have very high tolerances or very fine fit and assembly requirements. Prototyping, which is kind of the go-to use on all additive manufacturing machines, is going to be used throughout the machines. That's an application that fits both. For prototypes that require, again, high stress, high temperature, you're really on the FDM side. One application that I think gets overlooked, but as soon as it's pointed out that this is a possible route to take, engineers and designers and machinists get very excited, and that's the idea of using the FDM printers for jigs and fixtures. You know, a lot of companies out there machine these out of Delrin or aluminum, and they don't really need to be out of aluminum, right? We can print those jigs and fixtures, and we can do it much quicker and cheaper, and we get our parts faster, and we can continue on with the process. So jigs and fixtures is a huge application on the FDM side. Some more manufacturing related applications is sand casting patterns, also investment casting patterns, and patterns used for carbon fiber or fiberglass layup. A unique carbon fiber layup application is the idea of using a soluble core. So we talked about earlier the ability to print support material that's water soluble. On the production level machines, we can actually print entire parts out of that soluble material. So imagine if you had, let's say, a carbon fiber manifold that you needed to wrap. You wanted to wrap it in a single wrap to improve the aesthetics, but also to maintain the integrity of that fiber matrix. We can print that pattern in the soluble material, do our wrap. These materials on the FDM side are robust enough to withstand the pressures and the temperatures of the carbon fiber curing process. And then we can dissolve the pattern out once it's cured. And we end up with a pattern that's gone, but a part that's there in a single wrap, matrix intact, no no need for a clamshell mold. So that's a unique FDM application that I think is awesome. Also, low volume end use parts. So an end use part to us is a part that's printed and put into the final product that's eventually sold. So a lot of our printers have printed parts. They're end use parts. Another example is Airbus. Airbus recently put out a YouTube video talking about their end use ULTEM parts in some of their older airliners. The story behind that is they have the need for 100 or 200 parts a year. These were in the past injection molded parts, but the tooling for these has long disappeared. And Airbus hasn't really been able to justify the cost of creating new tooling. So they've actually turned to our FDM Fortis machines to print end use ULTEM parts. Hopping over to the PolyJet side, we talked about the idea of using Objet or PolyJet to print aesthetic concept models, marketing materials, really parts that need to look good when you hold them if you're going to have them in the hands of customers or in the hands of investors. There's some unique characteristics that we can only get on the PolyJet side, which is really important to know when you're talking about applications. That's the ability to print completely clear or transparent models. Also, rubber-like prototypes if you're going to simulate any overmolding or injection molded inserts or soft touch surfaces. And also, dental applications are really a PolyJet technology because of the accuracy needed and the smoothness needed. The best of both worlds. If you're getting into urethane casting or silicone molding or thermal forming, either one kind of works. Thermal forming is a cool application. Both parts produce porous models, and so it's very easy to pull air through our parts. So if you're doing thermal forming patterns, you don't have to worry about venting and trapped air. You can just pull air right through the entire part. Let's familiarize yourself with the machines. FDM machines, starting at the entry level Mojo. So the Mojo is going to be the machine up in the upper left-hand corner. Just a kind of a quick story about that Mojo image that you see. That's a standard image that I just pulled from Stratasys website. It's used in all of their marketing materials. But kind of a cool story about that is the outer housing that you see, the two gray parts. Those are actually printed parts that have been sanded and painted and then used in their marketing materials. And the story behind that is they wanted to get a jump start on their marketing materials. The tooling for those parts didn't exist yet. Those parts obviously didn't exist yet, but they were able to print those and paint those and get that material out ahead of time, which I think is a pretty neat use in the marketing field. The U-print is the machine in the I should say the Mojo has a build envelope of 5 inches by 5 inches by 5 inches, and it prints in ABS plastic. The U-print SE and the SE Plus, those are going to look like the machine in the middle there. They have an 8 by 6 by 6 build envelope or an 8 by 8 by 6 build envelope for the Plus version, and they also print in ABS plastic. The Elite and the two 1200 series machines, those are a little bit older models and they're being phased out, so we usually kind of gloss over those, but they're also ABS machines. The Fortis 250 is the entry-level production grade machine That prints in 10 by 10 by 12 inches in ABS plastic, but the big thing, the big differentiator at this level is the introduction of the Insight software. So Insight is a Stratasys software that's used to process the printed models on the Fortis level. It's a great software, it gives us a lot of control over the printed parts. At every level, we can control the density of the whole part, but at the Insight level, we can control the density of areas of the part. So for example, if I had a large part that's being prototyped, it's an injection molded part, I want to have the whole part hollow, but I'm worried about strength in some areas. Maybe it's some ribbing or maybe it's some bosses. At the Fortis 250 and above level, I can actually beef up only the bosses or beef up only the ribs, and I can maintain a very sparse density on the rest of the model, saving me a lot of time when it comes to print, but also a lot of material. That 250 is in the upper right-hand corner there. The Fortis 360 and 400 are very similar machines. The difference here is that the 400 is capable of higher heat materials. Okay, so at the Fortis 360 level, we start to open up the doors to some production grade materials, things like polycarbonate, nylon, ESD7. Okay, we start to see those options available. PPSF and Ultim start at the Fortis 400 level because it's outfitted for the higher temperature materials. Those two machines come with two build envelope options, a 10 by 14 by 14 small envelope option and a 16 by 14 by 16 large envelope option. Those are the machines that are pictured in the bottom left-hand corner. And then the big boy, kind of the flagship Fortis machine, the Fortis 900 is pictured there in the bottom right. This thing's a beast. It prints everything, and it has a build envelope of 36, 24, 36. PolyJet machines. The Objet 24, 30, and 30 Pro kind of all look similar to the machine pictured in the upper left-hand corner. These are the entry-level machines. Objet 30 Pro is really the most popular machine at this level. It prints in 8 different materials, prints in some clears, some rigid opaques, and it's a great little machine. It has a print envelope of, it's going to be about 10 by 8 by 6. They're given in millimeters, and I'm not very good at converting millimeters in my head, but that's about the size. The Eden level, the 260, the 350, and the 500, those are the machines pictured in the middle left there. These machines open up the door to the rubber-like material, and they come in 3 sizes. The only difference between the 260, 350, and the 500 are the build sizes. Those numbers, the 260, 350, and 500, that's the distance on the x-axis of the build envelope size. The Connex 260, 350, and 500 are very similar to the Eden machines. They have all the same material capabilities plus one. They can print the digital ABS, and the reason they can print the digital ABS and the Eden machines can't is because the Connex machines have 2 print heads. So they can print 2 materials at the same time. The digital ABS requires 2 materials to print. They're mixed together at the time of printing. But this also means we can print a character like we saw at the beginning, that halo character, with some rigid hard materials and some rubber-like materials all in a single print. The Objet 1000, the mystical machine, it's the pictured in the bottom right-hand corner there. Very large printer that has a build envelope of, it's about 40 inches by 20 inches by 26 inches. It's large. I would say the Objet 500 Connex 3 is the flagship PolyJet machine. It's not the largest machine, but it's the most capable machine. It's the same size as the Connex 500, but it has an extra print head. So you can print 3 materials simultaneously. You could do a rigid opaque, a rigid translucent, and a rubber-like material. You can also do full color and the Connex 3 level, and it's the only machine that has the color palette. So that's a basic overview of the FDM and PolyJet technologies. On the FDM side, we have thermoplastic materials, very well suited for commercial and industrial tooling and manufacturing uses. And on the PolyJet side, we have liquid photopolymers that give very aesthetic, fine surface finish, small feature models. If you have any questions about what I've said or what we've talked about, go ahead and shoot me an email at treid@goengineer.com. If you're interested in the applications, if you want to dive a little bit deeper into those, please check out one of our other webinars or shoot me an email with any specific questions, and go ahead and suggest an application specific video and I'll probably do it. I need some ideas. Thank you for watching. We're going to end the recording now, but we will shoot up a Q&A right after this. Thanks again for watching.